Hello. Today we'll be presenting about reducing the drag coefficient of an Ahmed body using ANSYS Fluent. For the physics of aerodynamic resistance, the pressure drag is driven by pressure differentials between the front stagnation point and rear wake, strongly influenced by macroscopic shape. The skin friction results from air interacting directly with the vehicle surface and boundary layer behavior. The induced drag is generated by 3D flow separation and vortices, heavily active around sharp edges and slanted surfaces. According to Chen et al. At year 2025, a 10% reduction in drag yields a 5% improvement in fuel economy. Moving on to the universal benchmark, the original Ahmed body, introduced in 1984 by S.R. Ahmed. The simplified geometry captures the essential flow features of passenger vehicles. It isolates complex fluid phenomena like flow separation and wake structures without the geometric noise of real-world automotive designs. The key parameters include standard slant angles, uh, either 35 degrees or 35 degrees. Another key parameter is the application. Wind tunnel validation, CFD turbines model calibration, and baseline testing for flow control devices. For the flow control strategy matrix, it consists of two types, which are passive control, where there is no external energy, and active control, which requires external energy. For each types of control, everything is listed in the table. For the diagnostic direction, passive geometric modifications remain highly practical for baseline drag reduction due to their zero energy requirement and structural simplicity. The apparatus and virtual wind tunnel architecture. Uh, it begins from the geometry creation, uh, where we use the CATIA software to draw the Ahmed body with a 25-degree slant, as that is the angle that we are using for the simulation. Next is the domain setup, where we use ANSYS design modeler. After that is the meshing, where we mesh the Ahmed body from a coarse sizing to fine sizing. After meshing, ANSYS Fluent is used to solve for the drag coefficient via CFD simulation.
Okay, hello. I'm Claren Veron. I will present for my slide. Okay, first one is the sixth slide here. Okay, all right. So before we jump into changing things up, we need to perform what I like to call a wake autopsy on our baseline model. We wanted to pinpoint exactly where our aerodynamic uses were happening. If you take a look at the velocity contour map, you can see the free stream flow accelerating right over the roof. But the real problem area is right at the rear slant. That's our primary separation point. Airflow completely detached from the geometry here, and once it does, it rolls into this massive alternating recirculation zone. What we are left with this huge pocket of low velocity, highly turbulent air trailing behind the car. The takeaway here is a simple: large, more turbulent mag means higher aerodynamic drag. So our main engineering goal for the rest of the project is to compress this volume as much as possible. Okay, we will move to the next slide. Took a look this from another angle. Let's map out the actual static pressure acting on the baseline profile. This gives us a really clear picture of physical force at play. Notice how we have the two total extremes here. Up front, we see a high pressure stagnation point from the air hits the bumper and velocity drop right to zero. That pushing the car backward. But look at the rear base. Because of the flow separation we just talked about, we get a several low pressure based suction effect. This exact pressure differential between the high pressure at the front and the low pressure vacuum at the back that creates a violent suction effect. This net gradient is the absolute primary driver of pressure drag on our baseline vehicle. Remove the next slide. Okay. So, how do we fix it? Fix it. Our geometry intervention was to introduce a passive 6-degree underbody diffuser angle upward from the vehicle flow. Now, from a methodology standpoint, we wanted to make sure that we were truly insulting this variable. Because of that, the entire virtual wind tunnel, the bonding domain, and the meshing setup using our validated 109 millimeter sizing, we keep identical to the baseline run. Our hypothesis here is pretty straightforward. By tempering the rear profile, we want to gradually guide the fast underbody airflow right up into the wake. If we can do that, we should be able to delay flow separation and promote better pressure recovery at the back. Okay. We move to the next slide. Okay. And look at the telemetry. The solver show a definite shift in performance. First, just to establish validity, both setup achieve identical numeric stability at our 10 power of -4 residual threshold. So we know that this highly reliable comparison. Let's look at the numbers. The baseline model gave us a calculated drag coefficient of 2.0474, but once we integrated that 6-degree diffuser, the CD dropped to 1.8701. Now you can visually see the difference in the contours to look at the dark blue low velocity core trailing behind the modified geometry. It is noticeably compressed compared to the baseline. The diffuser did exactly what it was supposed to do in the wake structure, giving us a stable and definite drop in calculated aerodynamic drag. That's from my part. Thank you.
For the geometry intervention, our intervention is adding up 6-degree underbody diffuser to the rear of the vehicle. We add a small 6-degree upward ramp at the back of the car floor to see if it improves airflow. For the methodology, the virtual wind tunnel and meshing setup will keep identical. We kept everything else exactly the same as the baseline test so that our comparison is completely fair. For the hypothesis, tapering the rear profile will gradually guide airflow and delay separation. We had set this ramp to smoothly guide the fast air from under the car into the back, keep it from breaking off into a chaotic mess. Chaotic mess. For the baseline geometry, the CD is about 2.0474, while modified geometry, the CD of 1.8701. The drag coefficient dropped noticeably as we add the diffuser, meaning the car moves through the air easier. Both setup achieve identical steady-state stability, resulting in a defined drop in drag. Both measure run perfectly smoothly. If you look at the blue color behind the car on the right, you can physically see that the turbulent wake zone is smaller and tighter. For the flow guidance, the 6-degree upward diffusive force underbody airflow to transition gradually. Instead of the end hitting a sharp drop off at the bumper, the ram guide it up smoothly. For the delay separation, airflow adheres to the rear surface longer, shrinking the recirculation zone. Because the air stick to the car body longer, it shrinks the giant tumbling pocket of that air at the back. Pressure recovery. The compressed wake reduced by suction. Shrinking the wake reduce the vacuum effect that try to pull the car backward, neutralizing the main driver of pressure drag. For the project synthesis and 50 vector, efficiency proven, the underbody diffuser successfully alters wake geometry and lower drag. The design worked exactly as intended, which directly helped save fuel. The telemetry anomaly. The absolute CD magnitude exceeds standard benchmark literature. While the drag is accurate, our total drag number of 2.0 is very higher than a real car, which is usually around 0.3. We will need to double check our reference area setting in the ANSYS solver next time. For the future vector, next test animation will introduce variable yaw angles. Right now, we only test wind hitting the car straight on. Next, we need to stimulate cross winds to see how the diffuser handle wind coming from the side. That's all from our group. Thank you.